recording's back rolling. We're closer to the end of class. Want to go and fill in some details here. All right, so one question I've been getting is there's something about like a bicycle tire rotating. You're saying like treated as a hoop, right? And that's this one right here. You guys see ring rotating about the central point? Because all the little spokes, yeah, it's a tiny bit of mass, but it's probably negligible compared to the tire. So this ring right here, you can basically treat as the bicycle wheel, right? Rotating about center, right? So mr squared considered points mr squared. That makes sense that the aggregate effect would also be mr squared about this axis. Now, here's the tricky thing. You guys remember this table, all these red formulas here, like something mr squared, okay, is only valid if it's rotating about the defined axis. You guys see every single one of these has some dashed axis, right? If you're not considering it rolling about that axis, then you have to apply parallel axis theorem. Isn't that? Okay. Now, here's why I want to mention this too, is that page in all the puzzles that I circled, the ones I picked from the book, the ones that I circled, are more, it's what I've been assigning the last few years. In the last few years, remember, AP has not brought in parallel axis theorem, so there might not be a good example of this in the puzzles that I assigned to you guys. Right? And so just be aware of that. If something's rotating about an axis that's not exactly aligned with this table, you have to add in the MD squared. Okay? Right? So take the table value, which is the I naught, and then add the MD squared. So for example, maybe a ball or maybe even a bicycle tire rolling across the floor, you have to consider, well, I have to take the table value, 2/3 mr squared. And that's if it's like spinning about central axis, like that bike tire I used as a demo the other day I was spinning. Right? But if it's rolling across the ground, right, maybe you have to consider, well, I have to add this extra mr squared. So it's like more inertia, right? Harder to get it rolling. And then once it is rolling, harder to stop it. Okay. Right. And that reminds me too of you guys remember all these balls rolling down these inclines, right? This is a classic physics question also, right? And I showed you guys there's two ways to solve this, and it's like the last minute of class yesterday. Two ways to solve it. What I'm calling the easy way is maybe conservation of energy, and the more difficult way is, well, you could consider forces and go through torque and solve it, right? And you should get the same answer if you do it correctly, right? Because notice these are the same solutions for the basketball, for example, right? Right. Do you guys notice that guys, which one of these do you have to include parallel axis theorem, and which one can you ignore parallel axis theorem in the technical solution? Okay, which one? Exactly. Right? It's just how this works out. So if you use the energy method, exactly what Asher said, is this particular method, you can just focus on the center mass of the object itself, the basketball, and you can actually bypass parallel axis theorem. Notice for the rotational inertia, I called it 2/3 mr squared, which is straight off the table for a spherical shell, which is what a basketball is. Right? Right. But in the torque version, you have to consider, well, it's rotating about this point down the bottom, and that's what's providing the torque. Hence, you have to apply parallel axis theorem. Hence, this jumps from 2/3 to 5/3. Is it? Which is in line with this slide right here. Is that the ball rolling? Is it? Okay. So this more difficult way to solve it, you can't solve it. They give the same answer. Right? Another detail I forgot to mention yesterday is, you guys see this friction right here? Okay. Now, remember last semester, we were talking about like, oh, if there's friction in a energy setup, like a car breaking to a stop, that would take energy out of the system. Is that the case? Guys, is this friction, which might be like a static friction to induce rolling, is that taking energy out of the system? No, it's not taking energy out of the system. All that friction force is doing is inducing torque, right? To have torque, really, you need two forces at two different locations on an object. Right? So I got this friction force and then this weight going through the center. See, those are acting at different locations on the ball. Hence, they can be torque. There's also a normal force, but that doesn't really cause any torque because it goes straight to the center. Right? So, yeah. So this is a static friction to induce rolling. Guys, if there was no friction, would that ball roll at all? No, if there's no friction, it would not roll. A lot of times with this, because these slides, I really just simplify and they leave off sometimes some assumptions, but a lot of times if you get one of these questions, it'll say rolls without slipping. Right, so there's no kinetic friction, because if there's kinetic friction, that would be taking energy out of the system. This should be really static friction just to induce rolling. Yeah, you can say.
So is that friction force applying the rotational kinetic energy?
Yeah, and there would be, right, some rotational kinetic energy, right? And that's this 1/2 I omega squared bit, right? Okay. So yeah, so recap this real fast. Okay. If you do the energy method for this, right, which I recommend, right, the ball starts off with all gravitational potential at the top, and then at the bottom, well, it's in motion in a linear sense, so that's 1/2 mv squared, but it's also rotating, so that's 1/2 I omega squared. So maybe if you start off with 100 joules at the top, some of those joules go to this, and some of those joules go to that. And if you know what type shape, then actually you could probably calculate what proportion that is. I don't know off the top of my head, right? Here, let's do this too while we're reviewing this. Guys, is this V, the linear speed of the ball, like you capture with a radar gun, connected to this omega, how fast is the ball rotating? Yeah, right. Is one increases, the other increases, right, for that roller shape with some radius. Okay. That's the next step. Do you guys see this omega I just replaced with the V over R? Ooh, right? You see it? Okay. All right. So here's a little reminder for this. All right. So close down this recording right here.